Hey everyone, welcome to Physics 40S. Dr. Carroll here. This is Unit 3, Lecture 2. We're looking at forces, this time spring forces or elastic forces. You find them in slinkies, you find them in pens, you find them in garage door openers, you find them in ropes, cords, anything that can stretch and then get back to its original location, its equilibrium, is an example of using Hooke's law. So Hooke's law, H-O-O-K-E, named after a guy Robert Hooke, I think his name is Fs, S for spring, equals K times X. Now some books write it as Fs equals minus Kx, the negative sign meaning a restoring force. Some don't put the negative sign in and just use it in words. So K is called the spring constant, so it's Fs over X. K is sometimes written as Ks. So the spring force over X, the units of force are newtons, the units of X, which is the stretch from equilibrium or the compression from equilibrium, would be meters. So the spring constant is called newtons per meter. Sometimes I call it a force constant because I'm thinking of the chemical bonds in chemistry, because you can think of a bond has like a little spring with the atoms oscillating, vibrating around their center of mass, and the word uses force constant, but I'll try to say spring constant most of the time. So it is a restoring force, not restraining force. It should say restoring. So here we have an example of a fish from a hook. So the fish is dangling from the hook. This is like basically a vertical spring scale, isn't it? So there's a spring which is going to try to get the fish back up towards equilibrium. So when those balance, we say that the gravitational force is the same as the spring force, and we relate that to the weight of the fish. Thicker, stiffer springs will have a higher K value, so your garage door springs will have a much higher K value than a spring on a common ballpoint pen. If I look at the MiniText here, I see an example of the fish there, and the spring force and the gravitational force are the same. Here's someone's jumping down from a cord. I would never do that, and maybe some of you would like to do that activity. It's pretty exciting. I think there was one where Rick Hansen and Rick Mercer, there's a video you can look at where they jump off a bridge attached to this rope, and that's pretty interesting. So the force of gravity is down and the cord goes up, and so it balances out. Here we have gravity and the spring force associated with your shock absorbers in the suspension of your car. Okay, there's a graph showing how the relationship comes from, and here's an example of, speaking of cars and things, you have a tire pressure gauge, an old-fashioned one. So the pressurized air, when you attach the head of the tire pressure gauge to the tire valve, is going to push out this little plunger and apply a force. So it's going to squeeze these together, and that's going to relate to the indicator, so you can determine if you need tire pressure or not. Let's say the spring constant was 300 newtons per meter, so that's given, so that's K. K equals 300 newtons per meter. And so the extension is 1.9 centimeters. And remember, convert that to meters, so 0.019 meters. What force is applied? So F equals Kx. So it's just 300 newtons per meter times 0.019 meters. And so the air applies 5.7 newtons to the tire pressure gauge. If you have a slinky or a spring which is stretched too much, you lose the distortion, and we've all seen that, and then the spring is useless. So be careful. You don't want to what do I want to do? You don't want to overstretch a spring, because then you have lost its resiliency, you've lost its restoring force, it can't get back to equilibrium. So here's some examples. find the unknown, and then we have, let's do question 2 first. A mass of 2 kilograms is hanging onto a spring stretched 4 centimeters from its rest position. Find everything else. So we're talking about a vertical spring. Horizontal springs, we'll get to that a little later. So here's a mass. It's 2 kilograms. It's dangling from a spring. So you got force of gravity, and then you got the restoring force, Fs, going back. Force of gravity is mg, so it's 2 times 9.8, which is 19.6 newtons. So then the spring force has to be 19.6 newtons. Okay, my x is 0.04 meters, so meters. So I can get my k, because k is f over x, so 19.6, or fs over x over 0.04. So I can get the k associated with there. 19.6 divided by 0.04 is 490 newtons, and we have the answer right there. These other ones here is really practice on metric prefixes. If I go to our example here, okay, we did the tire pressure gauge. Here you have page 181, 2A, 2B, 2C, and 2D. So they're all examples of just isolating for F, K, or X given the others and just getting the appropriate units. Page 189, 52, 53, 55, and 57. There we got the answers in. Why don't we try one or two of those? 52, 53, 55, and 57. Now, so I'm going back to the MiniText here, and oh, this is the end of chapter problems. So I'm just zooming down here. The answers, yeah, they're in the booklet, but they're also in the end of this MiniText. So okay, let's try 57 here. Find the normal force for a crate of mass 670 kilograms being pulled up by a spring with K equal 900 Newton meters if the spring is stretched 1.55 meters. Okay, so let's go back here and so the net force, we have the normal force and the spring force are going up and gravity is going down. So then the normal force is the force of gravity minus the spring force. The net force is 0, it's static equilibrium here. The normal force is the force of gravity. Force of gravity was 670 kilograms times 9.8. Is that right? Find the normal force for a crate of mass 670 kilograms being pulled up by a spring if the spring is stretched 1.55 meters. Okay, so we aren't talking about acceleration yet. We're assuming static equilibrium until we get more information. So that is 65, 66. Now the spring force is 1395. How do I know that? We have that the spring constant is 900 newtons per meter, and it's stretched 1.55 meters. So that gives me 1395. So then my normal force is 65, 66 minus 1395, which is 5171 newtons. Okay? And I'm going to let you try the other ones on your own and then ask me if you have any questions. So you may think, spring's not such a big deal. Well, if you like pogo sticks, it is. And if you like aircraft carriers, it is, because you can use these big ropes to help brake a plane when it's landing in the middle of the ocean on an aircraft carrier. And you can find some videos, which is pretty cool stuff about aircraft carriers and elastic forces. So yeah, try those questions. I don't know why that's written there. Get rid of that. On page 189, 52, 53, 55, 57. and take a look at a video or two on YouTube. Just Google Hooke's law, and you'll find that this is certainly a helpful thing. And I really like question 57 because it has gravitational force, normal force, and spring force all together. Okay, so that is good for that lecture, and we will talk about inclined planes next time.